Hello everybody and welcome to our tutorial regards electromagnetic waves. The time that we have been waiting for just arrived. And I want to tell you something. In 1800s, a person named William decided to measure the temperature of each color. He put here a light, he put a white light and then split it to its color. And that direction, and that direction, and that direction, and that direction, and last one, reference to see what is the light inside the room, right? And then when he measured the temperature, he saw something really cool. He saw that there's kind of increasing value of temperature as you go with the colors. And the red is really hot. And then he saw something that he would not forget. He saw that even this one have temperature. And then he said, oh fuck, there's actually light that I cannot see, that I am blind to it. And to feel a little empathy to this scenario, I put this video for you, so you can put the camera to the TV.
Oh my god! Holy shit! What do you see?
Do I look better looking?
You look weird. You look nice on you.
Wow. It's weird. I don't know how to explain it.
What do you see?
The houses, like I can tell what color they are. Like that one right there.
Yeah,
that one right there is brown.
Yeah.
That one's red.
Yeah, you're right.
I did not know these are different colors.
Yeah. What about this nice purple bush?
This is a funny. I'm not sure I know what this color is. Is that orange?
Yeah, it's like a mustard.
Did somebody painted that house orange?
Bird? Here, come here. Let's walk over here.
Purple's beautiful.
Yeah.
I've never seen purple before.
Really not even like a shade of it?
Yeah. That's purple, right?
Uh-huh. Stop sign, red. Stop sign.
What?
Okay guys, so what I want you to realize is that right now we are actually embrace ourselves inside a zoo of colors that we actually can't see. Okay, so this is the visible light and we know the range like the rainbow. But above the purple we have the ultraviolet. Above the violet, which is the same radiation that when you go to the beach you put sun cream and sunglasses to get protected. More energy you're going to get to X-ray, which you're going to talk really deeply about that, and more than that radioactive. Okay, and even below the red there's a color which called infrared, the sub-red color, which we cannot see, but many animals actually can use this color to see where are there's animals that they can hunt, right? Snakes and stuff like that. And Wi-Fi, right now there's a lot of Wi-Fi wave we cannot see. We don't see the colors, okay? And on and on and on. And I brought this demonstration to you. So you cannot see the wave, but it's there, okay? Let's give it a few seconds. Okay, what I'm doing right now, I'm shifting this wave to a sound wave. This is the sound of the wave. And the wave can go through stuff, like myself, but it can... Okay, less volume. Okay. it's a go-through stuff, maybe it's a little bit harder, and I can block the wave, like I can block the color, the wave that go through you, right? And it's not only depending on the material, but also the direction, okay? So that's what we're gonna talk today. Let's close that and that. And we're gonna jump into the question about X-ray. So me and my cousin really love to do skateboard. You didn't do physics 1 with me, so you don't see the demonstration of skateboard yet. But sometimes, you know, you fall for the skateboard and you probably broke your arm. Yeah, that's what happened in this risky extreme sport. So we're gonna take my cousin. What? I saw it. Ah, you saw some of that? Okay. So my cousin needs to go to the hospital, and we're gonna take him to the hospital. And in the hospital, they have an X-ray machine. And the idea behind X-ray, this is electromagnetic wave that can go through your body, but not through your dense bones. And that's the reason we can see bones, okay? Because it's reflected back to us. Good. So let's deal with that. So in X-ray machine, X-ray device emits this kind of wave, right? How we write wave? So it's gonna be electromagnetic wave. So I put here E, right, as a vector. And wave is a phenomena. It's a disturbance in space and also in time. It have a magnitude. This is gonna be the magnitude of the X-ray. Be careful, it's really dangerous, okay? This is a really high, this is really dangerous. Epsilon node, and the wave is changing in this manner. Sinus, and in, let's put here space, and in what direction the wave is at the Y direction, okay? This is the propagation of disturbance that we have in the electromagnetic wave. And I want you to notice something. Here, I'm going to put K. K is the wavelength. K is the opposite idea of the wavelength. We're going to talk about it. But it determines how much space play the game in this sinus. Okay? And here I have omega, which you already know, omega t, which tell how much time play in this sinus, right? And we also have this term, which is phi. What is phi? Phi is actually a correction to the sinus, okay? Think about it. What is actually sinus? Sinus is actually, you are nothing, you are zero, I don't care about you, and then suddenly it becomes strong. And cosine, on the other hand, is the strongest, but I know that with time it's gonna die out, right? So phi is just here to correct and say, maybe it's not a sinus, maybe it's cosines, maybe it's something weird, like -1 is nothing really, it's the opposite of something, and then it's become 1, okay? So maybe it's something in between, right? So this is the idea of phi, is a correction in radians that's gonna fix this to the certain value that we need. So I'm gonna tell you that in time, in the specific space 0, where we shoot the X-ray, and in the specific time t equal 0, this value was 0, okay? And I want you to find what is phi, okay? Yes? So let's do it, okay? So this is gonna be our first question, 1A. So it's really easy. I'm gonna just take that, put it inside. I know that E at 0, 0 equal to what? To the magnitude sinus of 0 minus 0 plus phi equals 0. I don't care about the magnitude. I can divide it, some positive number. And I get the question, a new question, when is sinus equal to 0? So let's draw a sinus. I don't know when. Sinus is that, right? And it's equal to 0 in many places, right? Actually, phi can play as n multiplied by pi, right? Every pi, boom, 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 I'm getting 0 value. So this is not enough to find phi. And the reason is because you need another thing. You need to know how does the electric field of the X-ray change in time. So I'm going to tell you that the derivative at time 0, location 0 was positive. Okay, I turn on the device, I want the radiation to get out. Okay, we have another term. I'm going to this side of the board. Goodbye, TV. Okay, good. So I'm going to use our second term. What is the derivative of our electric wave? Magnitude stays the same. What is the derivative of sinus? Cosine, exactly. Inside, we're going to have the same. I'm going to do these two dashes, okay, to remind us it's the same thing. But I need to pull out something, which is minus omega, right? Good. And great, we have that. And they told us that this thing in time 0 is equal to what? It's not equal to 0, it's positive. It's bigger than 0, right? Put your bigger than 0, right? So at time 0, this is cosine of 0 plus 0 plus phi. Yeah, multiply minus omega, right? And this bigger than 0. Okay, I can divide by that, which is going to flip this term, right, to the other one, to be that, right? And I got a new question. When cosine of phi actually smaller than 0? I don't know, but let's draw cosines. So if I'm going to draw cosines, I'm going to see that. Up, up. Okay, this is positive, and this is negative, right? So this is pi over 2, and this is 3 pi, but I really care about what? About jumping in pi, because I know something. I already know that phi is n multiplied by pi. I still don't know which one. But I see here immediately that, haha, this is going to work out, right? So I can say that phi, using that and that, phi is equal to pi. I know how this wave is actually behaving. Okay, good. So let's clean the board. Let's go here. Okay, I'm going to clean that. By the way, the name of the guy that did this experiment called William, if you want to read about it. Okay, I'm going to leave the bone. Good. So the next question is I want us to draw how the wave look like. Okay, how all the machine look like. So we have here my ankle on skateboard, of course. Here it is. And you know that if it's my ankle is really cool. So here is his broken hand probably. This is his face. Playing cool, I don't feel any pain, right? You have its hat. Like that, right? And this is the gun of the X-ray. Okay, this is the axis where we put it. So this is X direction, this is Y direction, this is the Z direction. So we're gonna shoot an electric magnetic wave. So in which direction the electric magnetic is? At the Y direction. So the electromagnetic wave changing its value in the Y direction. So it's actually down in the floor, only in the XY, okay? So it's looking like this. Hop, wait, sorry. It's that. Ha! Yes? So that's what we have. You see it? So at the beginning it's negative, the electric field. If you're going to put phi and 0, 0, because sinus of pi is actually start to get negative. Let's go here. This is pi, right? So I know that the value going to start as negative. So I look at the y and I said, okay, I need to go to the negative side. And here I get to my maximum value, which was E node, right? Which actually minus E node. And here I got to my maximum value, E plus, right? And then it's continued that fashion to the hand, okay? Good. So we drew it Really nice. So what is the direction that the electromagnetic field actually propagate in time? X. Good. And you can see it here, the equation, where you are propagating at the X direction. Okay? Good? Cool. So let's clean that. We're going to ask, so what is the direction? Let's be more precise about it. What is the direction? What is the direction? Which the wave is propagate. Okay? So the answer to that is that K direction is at the X. So K actually tells us what is the direction of the electromagnetic field. Okay? Cool. And where is the electric field change? On which value? Is our y-axis, right? So now if I'm going to ask you in which direction the magnetic field actually taking place, because we know, according to Maxwell's equation, that light, the visible and the non-visible light, actually is two phenomena. It's electromagnetic wave, in our case that one, and also a magnetic wave that's going along in the K direction. Look at the choreography that I did here. Okay? So that's what's actually happening. Okay? So what I want you to know that if you know two of them, you already, it's hard to practice that. Yeah, it's really hard. It's really hard. Okay? And it's more hard than you think because they are two in phase. What do I mean by in phase? When this one eating lunch, this one eating lunch. When this one need to go to the toilet, this one need to go to the toilet. What I mean is that when one is maxima, the other one is maxima. When one is zero, the other one is zero. Okay, so it's like this. Okay, that you see me? You understand what I did here? So it's kind of that thing. They're same zero at the same time. So every time you see electromagnetic wave, you need to remember this. Okay, I do it in purposely crooked. Okay, this is 90 degrees angle. Okay, so if you know the direction K, right, this is the direction E, the cross is the magnetic direction. Okay, and I already told you something really cool about that. Let's write it here. What is the wave function of B? Right? What is that? So I'm going to tell you. Okay. So B xt, it's going to be in what direction? So x, y, we left with the perpendicular z direction, right? Okay, we have here something that relates to the magnitude, and we have here sinus, but the sinus is going to be the same. Okay, I'm going to put two dashes, which mean I copy kx minus omega t plus phi. Okay, it's the same, which means the waves are in phase. When one is maxima, the other one is maxima. One is minima, the other one is minima. Zero, both in the same time and same place in space. Okay, so what is this thing that we have here? What is actually B0? Okay? To understand what this equal to, I want you to see that. Okay? This is the magnitude of electric field, and it's equal to the magnitude B0, okay? But there's a correction constant between them. Okay? Remember what are the units of each one of them? What are the units of magnetic fields? Tesla. Tesla is a gigantic unit, okay? If somebody came to me and said, dude, I got 1 Tesla, I would look like that. Are you kidding me? Like 1 Tesla is insanely big magnet, okay? Usually when we talk about magnet, we talk about small number, millitesla, right? This kind of thing. But 1 Tesla, 7 Tesla can kill you, okay? It's really dangerous. Okay, you are not allowed to use 7 Tesla in hospital. Okay, But electric field, it's volt per meter. I can take 100 volt per meter. This could be 100. This could be things that are huge, right? So which big number I know that can help this tiny number to actually be equal? And the crazy thing is speed of light. Speed of light is actually the correction factor between magnetic and electric. And that was astonishing discovery by Maxwell, okay? So this constant is actually equal to E, which is a huge number, divided by C. Now it's got Tesla unit, and it's a small number, so that's what we have here. And let's draw in green the magnetic. So the magnetic is the same concept as the electric, right? It's gonna go to the minus because it's in phase, right? So it's gonna go to the minus Z, and then it's gonna go to the plus Z, and they're gonna meet each other at the 0 point, right? So this is what happening. Do you feel me? You got it? It's propagated the x direction, yes, x because we have here kx, right? But it's changing in the z direction. Really good. We got it. Okay. Now I want to talk about new concept. I'm going to go there. A new concept, which is what is the Poynting vector of this radiation. Okay, it's a new concept, but it's going to be really intuitive to you because it's kind of like a solar panel. So my question to you, what is this vector equal to? And there's a formula to that, which is E cross B divided by mu 0. And in physics, when you ask what is something, you really care about what are the units. And the units of this thing is watts per meter squared. What are the units of watts? Funny. What are the units of watt? Huh?
Watts.
Yes. What is that? Watt is equal to what? To, this is power, remember? Which is joule per second. Remember, it's really boring to talk about joules, right? How much money do you earn? $100. In what time you earn $100? That's what we really care about. Bill Gates earns $17 per second. Oh, this is a lot of money, okay, right? Just till my end of my sentence, he did a lot of money, right? This is the concept. So this is watts. But when we're talking about radiation, we really care also about the size, right? If I have a big solar panel, I can gain a lot of watts, right? If I have a small solar panel, not that much, okay? The same thing goes with my ankle hand, okay? It's standing there next to the radiation. How much area it's have, it's how much energy it's going to absorb from this radiation. You feel me? Good. So let's solve this thing. In our class, they always 90 degrees to each other, right? So this is actually E xt multiplied by B xt, right? And the cross gonna give us what direction? K. E cross B, you see it? E cross B gonna give us K direction, right? So this is gonna be the K direction. Let's put here that joule sec meter squared. Cool. Divided by mu 0. So let's put each one of them in place. So E is actually E0 multiplied by sinus of something, right? B also have the same minus. So we're going to put here square. And what is the amplitude of B? Is E node divided by 0. So this thing actually can get square and C at the bottom multiplied by mu. And this is my Poynting vector of this wave. Okay? Good. But I want right now to emphasize something. I want to talk about intensity. Okay? So what is intensity? Intensity is like counting the money. Okay? It's like how much, it's joule. Okay? It's how much energy do I have? Eventually, talk to me business. How much money do I get from that deal? Okay? And other question, how much heat is the hand gonna absorb from this radiation, right? Okay? So what we need to do to the pointing vector, the solution we have here, in order to have this one, okay? Use the units. What we need to do, I see here only joule, and what I see here?
Joule over second meter.
So we need to get rid of these two, right? This one and this one. Okay? So how we can get rid of the meter squared?
Multiply by area?
Yes, multiply by area. If we want to be precise, we're going to do area integral, right? But if it's just in the same direction, right, the hand is not like going that direction, everything is smooth, it's just going to be A0 multiply by, leave here a space, okay? S, right? Okay, leave here a space, okay? S. And S is a function of t, right? Of the time. Right? X and t actually, right? X and t, space and time. The opposite one. X and t, and it's a vector. Okay, good. So now I want to ask you the question, forget about the vector, just the magnitude. Okay? Now I want to ask the question, okay, how are we going to get rid of time? What?
Integral?
Huh? Integral is a good answer, but I think it's not intuitive to say it, right? So we want to multiply by the time, right? That's what we want to do. Look, this is a sinus, right? Sinus gonna do something, get to the same point, and what it's gonna do again? The same thing, right? It have a time period. So instead of see what's going on all the time, we can say what's going on in one period, and then multiply it by how many periods that you have in your problem. It makes sense that if I'm gonna be in the microwave for 1 second, I'm not gonna get heat. And if I'm gonna be there for 10 time periods, maybe I'm gonna be cooked, right? So this is the concept. Now you can play with it. So we need to understand what's going on and to do an average of time, okay? So let's remind you how we do average, okay? So if you want to do average of the height in the class, so this is the more mature way to write average, because this notation of vector is already being taken, right? So what we're going to do, if I want to measure the heights in the class, I'm going to sum the heights of everybody in the class, right? And going to divide by how many people I have in the class, right? 1, 2, 3, 4, 5, right? That's what I'm going to do. But time is a little bit more tricky. Time is not like that separated things. Time is going by, right? It's smooth, right? I cannot measure time in that precision, in that kind of thing. So what we're going to do, we're going to sum, we're going to do an integral of time, okay? And you're going to multiply by dt, and we really care about what's happened between period time, and we're going to divide by the total time. So what we actually did is we see what happened to S in a specific time, right? At the beginning, dt, and then the next dt, and then the next dt, and then the next dt, and then eventually I finish when I got to one time period and divided by the whole sequence of time that I measure. So this kind of thing is a more mature way to do average, okay? So that's what I did over here, okay? So cool. So we have this thing, we just need to plug it in, right? So the joule that I have in one period of time is A0. These are all constant, I can get them out, right? I can get them out, divided by C mu. And I'm gonna let you know the result of this thing. If I'm gonna do here an integral, 1 over t integral of sinus square, right, dt, right? If I'm gonna do that, the solution for that would be half. So this is gonna be, in the end, half. Okay? And you're gonna see it in the lecture, but you can also do it yourself. It's really an easy integral, not that hard. Okay? And I recommend you to have in your notes for the exam this identity, okay? Good, so we found the intensity, really, really good.
Don't we need to multiply by the number of cycles?
What?
Don't we need to multiply by the number of...
No, it's per specific time, okay? It's like average, okay? I like assume that everything happened the same thing on each time period, okay? So what right now I want to do is right now we just did an easy peasy electromagnetic question, okay? What's happened right now is the nurse in the hospital came by, okay, and gave an elbow to the x-ray. And now the direction gonna be messy. And this is more like the thing that you're gonna see in the exam, okay? A more challenging direction problem. But everything that we talked about gonna be the same. So we're gonna clean this. So right now, because of the punch that the nurse gives to the x-ray beam, okay, the direction of the gun is that. Same magnitude, but right now cosines of alpha 2x plus y, let's do here that kind of bracket, plus omega t in the direction, oh my god, x minus 2y. That's what we have here, okay? So what I want to ask you, what is our k vector, the wavelength? And not the wavelength, the wave number, okay? This is wave number, and the reason I always confuse between the wave number and the wavelength is because they are really connected in that manner, okay? This is the formula that connect them, okay? So, how are we going to do it? So what I want you to know, that here in the really proper way to write the argument of electromagnetic wave is that fashion. It's k vector dot space vector minus, not plus, minus omega t. Okay, so that's the formal way. And we are really care about this term right now. That's what they ask us, right? Good. So what we can do, we need to give this thing, we need to take this thing and shift it to look like that. That's what we need to do, okay? So how we can do it? First of all, I see here plus, and what I want here to have? I want minus. So cosines can do that, right? Cosines is actually minus theta equal cosines theta, right? Even function, right? That's the idea. Okay, let's look at the mirror, which is the y-axis, and you see the same, right? Right? See the same in the mirror. Good. So we can do this trick, right? So no problem. Let's do that, and that's going to give us one step closer. So let's put here minus alpha 2x plus y minus omega t. Didn't change everything. Okay, good. Now I want here to, right? We want to have dot between these two vectors. So here I see that this term is minus alpha minus 2 alpha x plus, sorry, not plus, minus alpha y, right? Plus 0 multiplied by z. I don't see z, right? I don't see it. Minus omega t. And now this thing, it's really easy. This is x, y, z. And here I see minus 2 alpha minus alpha 0. You see it? This is our k vector, and we can write it even more nicely, which is this direction. Minus outside, alpha outside is 2, 1, and 0. We found our wave number. Yes. What is the size of the wave number? How we can find the size of it? what we can do? What is the size of it? I'm just gonna square everybody, right? That's the way to do it. So if I want to find the size of it, I'm just going to square, right? But of this, like 4 alpha square plus alpha square plus 0 square, right? And this is gonna end up to be alpha square 5. So this is the magnitude of this vector, right? And if I want to find lambda, the wavelength, what I need to do? Lambda equal to 2 pi over k. So 2 pi divided by alpha 5, right? And you can find the wavelength of X-ray, right? And you also have frequency. If you want to find the frequency, how you can do it? Using the formula V equal lambda f, right? And for light, this thing is actually speed of light, right? C. So this is C divided by lambda, which is C divided by 2 pi multiplied by alpha square 5, right? If you want to do that. Good. Now I want you to find what is the direction of the magnetic field. Yeah? What is, no direction, what is the vector of B? How we can do that? So you need an equation, right, which is that. At the previous case it was easy. I told you that E cross B, right, equal to the direction K. This is still hold, but your X and Y is like kind of that, right? Kind of a messy. Okay? So you need a general idea. So the general idea is that if you want B, first of all, you need E, and it's gonna be the cross of who? K cross E, right? K cross E gonna give us B. You see it? But what is missing here?
Correction term.
Correction term. This magnitude, this is units of volt per meter. This is Tesla. This is insane, right? And this is 1 over meter, okay, kind of thing. So we need this to be corrected, 1 over C, okay? We got it? Good. So that's what we need actually to do. Okay, perfect. So let's do that. How we can do the cross, okay? How we can do the cross? Just a reminder. So the cross is, I'm gonna do determinant x, y, z, right? Here I'm gonna put the first term. This is yc outside. K, what is the vector K? Is minus alpha, right? Sorry, it's minus 2 alpha, minus 2 alpha, minus alpha, right? 0. Who is E? E have, in our case, 0 contribution at Z, right? And you have 1, yes. And it's have 1 here, minus 2 here. Sorry. Yes, 1 minus 2. And here outside, I can put the cosines, right? Here. So here I'm going to put this, the magnitude, cosines, this thing, right? That's what I can do, and I need to solve all of this, right? Good. So I'm going to save us time, okay? I'm going to save us time, and I'm going to write here that the solution that you need to have is that, if you did the cross well. At what direction? The Z direction. Okay? Which makes sense because it's perpendicular to the electric field and also to the magnetic field. Okay? Good. Sorry, this is the magnetic field. Perpendicular should be to the electric field and to the wave number. Good. Okay. Another really easy question I want to do. Okay. So if, for example, you can stop the video and we can start a new one.